Welcome back. It's essentially a continuation of the last lecture, 12th lecture on the series on Riemann integration. But before we go to the theorem, I just want you to reflect upon what we did in the last lecture. You may remember I asked one question: where did we use alpha is increasing? If you've gone through the proof, you would have seen that we don't require alpha to be increasing. We wanted only alpha to be differentiable, and alpha dash, the derivative of alpha, is integrable for the proof. And second thing you must have observed is something very interesting. In that proof, the proof will become extremely simple, and in some sense most general statement one could ever make, something like integral f d alpha equal to integral f alpha prime with various conditions on f alpha, etc. We got the best deal there because we were ready to use both the definitions. I wanted to prove f alpha is integrable using Riemann sum, right? And I also used Riemann sum for f times alpha dash, but to have a control over something like alpha dash s minus alpha dash t in modulus, I used Riemann criterion. That is the Darboux sum approach I used there. So that's something very interesting. See, this just shows why you should not hesitate to use equivalent characterizations or definitions. It may make your life simpler, and you may even get a better deal as we got here. Okay, I hope you appreciate this. So in today's talk, what we are going to do is, do you remember I said there is a very general version of integration by parts formula applicable to Riemann Stieltjes integral. The standard one we used was using fundamental theorem of calculus only for Riemann integral, but there is a much more general version. Okay, that's what we plan to do today. Okay, stay tuned, we will go through the proof. So let us get started with the proof. So recall what we want to say is, let us recall the integration by parts formula fg, under various conditions. Let me not worry about for the timing. It's fg integrate, that is fg at b minus fg at a minus integral g f dash here to b. This is the very general version. Okay, that we proved assuming f and g are continuously differentiable or whatever it is. We deduce it from fundamental theorem of calculus. So today what we want to prove is the very general version, that is, let f and g, okay, this is the theorem we want to prove, be bounded functions from a b to r. Alright, okay, assume they are bounded functions. Okay, assume that f belong to R of g. What does it mean? Integral f dg makes sense. Here to be, of course. Okay, exists. Okay, this is the hypothesis. Okay, then what we want to conclude is g belong to R of f. There is a symmetry, that is integral g df exists. And what's the next thing? How they are related. How are they related? It's exactly similar to the way we wrote, that is integral f dg, okay, equal to g of b, f of b g of b minus f of a g of a, okay, minus integral a to b, this is a to b g df. This is what we want to prove. Okay, one sometimes writes as a symmetric way, a to b f dg plus g to a to b integral g df equal to f g at b and f g at a. Okay, anyway, and notice that this is a complete symmetry. There is, okay, right. Now we want to prove this. The proof is easy, not difficult. Okay, I will simplify the proof with under some simple assumptions. Okay, and right, so what we want to do, so right, so now we want to prove this fellow. So let us look at fg. So integral f dg exists, right? Call it a. right? So what does that mean? So I want to say integral g df exists, and I know integral g df exists, and it's equal to something, namely what is it, a minus fg this, right? This goes to the other side, therefore I hope I wrote it correctly. This, okay, the other way around. So let's not worry about integral g df exists, therefore it must be equal to fg at this minus integral f dg. I hope I got it correct. Okay, this equal to this. Yeah, just interchange these two things, I should be getting, yeah, right, okay, right, okay. So as I said earlier, should I have Riemann approach or Darboux approach to prove integral d g df? Notice that first I did not assume anything to do with the f and g. They may not be increasing. When I want to say integral a to b g df exists, I am not assuming f is increasing. Therefore naturally Darboux approach is ruled out purely by because of our hypothesis. Even otherwise, notice that I already said if I know the integral equal to something, then its Riemann sum may be easier, right? So what I should want to start with is the Riemann sum. So let us look at epsilon with positive given. Since f belongs to g, f is g integrable, then what do I know? I know there exists a partition P, so that for every partition Q which is finer than P, and for every set of tags, yes, f p t g minus a is less than epsilon, right? Okay, now let's look at, yeah, just play with it, just don't go through a proof, right? What is this object? This object means this is summation something like f of ti and g of xi minus g of xi minus 1. Is that right? I equal to 1tn or whatever it is. Yeah, I know what do I want. As I already said, I would like to say, I would like to take the Riemann sum approach to this may be at the q, okay, q t and f. And how does this will look like? This will look like summation g of ti f of xi minus f of xi minus 1, right? Riemann sum for this will look like this. Now notice these two things. Something is very interesting, right? F when it acts on ti, g wants to act on ti. When g wants to act on xi and f wants to act on xi. Okay, there is a kind of duality. You understand this? Yeah, so that means I have to go from the Riemann sum here, from this Riemann sum, somehow I have to go to this Riemann sum. How do I go? Is the question clear? Yeah, so that's where a little bit of thinking will help us. Okay, so what it means is, let us do, okay, I have a to b, okay, let us have something like x1 etc, xi minus 1, xi and xn minus 1 etc, right? So I have a ti here, right? From here I want to go here, so just notice that I want g of ti minus g of ti minus 1, okay, g of ti, but then I want f of xi minus f of xi minus 1. You look at this, do you get some idea how to do that? Yeah, the idea is that let's start with the q, which is a partition consisting of the original partition x1 to xn and the union of tags t1 to tn. So what are going to be my tags now? My tags are going to be all these fellows. Okay, there may be somebody here, t1, that will also be a tag, and there will be tn that will also be tag. Oh, sorry, it's a node, not tag, node. You understood this? Yeah. So what is the partition I'm considering now? I'm considering the partition A less than T1 less than X1 less than T2 less than X2 and so on, and Xn minus 1 less than Tn less than B. This is the partition Q I'm considering. Yeah. Is it okay? Right. Now, but I also want tags. What are the tags? Okay. Now the tags are very interesting. So for simplicity, we are going to assume my partition is something like A, X1, X2 and B, and the tags are T1, T2 and T3. Okay, you understand this? Right. Yeah. Now what are the tags for this partition? This is the partition now. A to T1, T1 to X1, X1 to T2 and so on and so forth. So how many subintervals are there? 6. 1, 2, 3, 4, 5, 6. Similarly, more general, you can do that. Yeah. Okay. Now for A to T1, I want a tag. You understand? The tag, so let me just use a different color. The tag is going to be this. You understand that? Therefore yes, I will use a different thing later. Now for T1 to X1, the tag is going to be X1, and X1 to T2, the tag is again going to be X1. Do you like this? Yeah. And T2 to X2, what should be the tag now? Can you guess? Yeah, X2. And X2 to T3, the tag is again X2. And now T3 to B, what should be the tag? I'm sure all of you know that. It should be B. Yeah. So what are the tags now? The tags are going to be A, right? X1, again X1. You understand that? And you understand that A, here X1, this is X1, here it is X2, and here also X2, and then B. These are the tags. Is that clear to you? Now can you do the general case? Okay, I leave it to you. Okay, do it on your own. Okay. Okay, pause, review, proceed. So my Q is this new partition. What is the Q part? This is my Q, and the set of tags is this, right? Remember, my Q I'm going to take on the simplest case so that you will see the idea clearly instead of getting to too much of notation. Therefore, what do I know? Because of my condition on the choice of P for this Q, and for this in place of T I am writing going to S into S. Okay, this Riemann sum will be less than epsilon. That is, let me write it. It may be easier for you to understand if I say this: Q and S is the thing, and G minus A, that is less than epsilon. This is by hypothesis Y. Q is finer and S is a set of tags for this. So what all I have to do is very simple. I try to write down this. Now it's pure algebra. Yeah. So what I want to do, I want to write S, F, Q, S and G equal to what? Let us do that. Okay. So this is equal to, it may be easier if I have this in front, but unfortunately my monitor doesn't allow, so let me again write it. A, B, this is X1, this is X2, this is T1, this is T2, this is T3. Did I do that there? Yeah, correct. Yeah, right. Therefore, what is the first one here? What is the tag here? The F. Therefore, it's F of A into G of t1 minus g of a. Okay, you understand this? Plus next, for this interval I have to do that. That is going to be, what is the tag? F of x1, because remember the tag. Okay, maybe I should again use it. This is the tag here, and this is the tag here, and this is the tag here. Yeah, and this is the tag here, and this is the tag here, and so on, and this is the tag here. This is for my own thing, f of x1 into g of x1 minus g of t1. You understand this? And what is the third? See, there are 6 intervals, right? So six sub intervals, so I would write for all of them. So I have done these two. Next one is x1 t2. That is going to be, what is the tag there? The tag is going to be f of x1 into g of t2 minus g of x1. Okay, so I have done this, I have done this, I have done this. Okay, plus third one. Okay, this is done, so I have to do t2 x2. Therefore, what is the tag there? F of x2 into g of x2 minus g of t2. So I have done this also. Yeah, so you just have to write a very general case in the, if you are worried about. Okay, are you following this? I have done 1 2 3 4. Okay, now I have to write the fifth one. That is going to be, what is the tag there? Again f of x2 into g of t3 minus g of x2. Am I correct for this? Okay, and what is the last one? That is f of b into g of b minus g of t3. So all the 6 terms I have done. Yeah, now you can rearrange them. Remember what was our idea? Go back, you will see how we are going to, from this sum, this Riemann sum with f and g as the integrator, we want to move to the Riemann sum for g with f as the integrator. So I have to correct f of g of t1 something. Okay, now see that you get that. So you have g of t1, right? So g of t1, let's look at those terms. G of t1 is here, g of t1 is here. So what do I have? G of t1 into, this is f of a and this is f of x1, right, which is a smaller. Let us look at that, t1 and x1, therefore t1 is smaller, right? So g of x1 must be bigger side, so we will do that. Okay, are you following what I'm saying? Therefore I will write it as minus f of x1. Okay, and this is minus of minus, therefore it is a plus f a. You understood that? Okay. Okay, remember FAJ will still remain with a minus sign. Let's not worry about it. Now I have to look at GT2 term. So let us use a different color scheme. GT2 comes here and G22 comes here. So what do I have? GT2 times minus fx2, yeah, plus fx1. Yeah, so you follow that. Now we want the last one. So GT3 and GT3. So what does that come as? GT3 comes as GT3. Okay, this is okay, minus FB. Yeah, is it clear? Minus FB plus fx2. Is it okay? Now what are the terms left over? See, minus FAGA, that is left over, that is minus FAGA, and plus FBGB, this is left over. Okay, if you want I will use a different thing. Okay, these are things left over. Okay, now what happens to fx1 gx1? You can see fx1 gx1 cancels. What happens to fx2 gx2? fx2 gx2 cancel. You understand this? So this all I get. Yeah, but what is this? Now we are through. Now what is this? This is of T1 into this is delta F1 with a minus sign, therefore minus of delta F1. Do you understand this? And this is GT2 into minus of, therefore minus of delta F2. Okay, let us put everything plus now, and this is GT3 into minus of delta F3. Yeah, because this should be x1 minus a, and similarly f of x2 minus f of x1 and f of b minus f of x2. Did we get that? Yeah, we got it. You understood that? And plus, let me simply write fg between a and b, okay, so that I can save some pain in writing. So what have we got? This, what is this fellow? This fellow is minus of s of g with respect to what partition? The original partition p or whatever q. Okay, remember I just kind of call this as q. Okay, original for every q this is true, right? So start with any q, okay, with x0 to xn. Okay, and if you want, call it any p1 which is finer than p, and let q equal to this. Okay, so I am writing with respect to that p1 now. Are you following? I'm sorry for the notation, but I think if you know how I do mathematics, by now you should know this, right? Because unfortunately I chose this as q. Maybe you can write as q1. Okay, keep this as q, keep this as q1. All right, so this is fq1. Okay, so what we found out was this fellow is nothing other than this. Yes, q, and with respect to t and with respect to f minus fg at b. Yeah, I hope I did it correctly. fg at b, this is plus sign minus sign, right? Okay, so what we found was s of f q1 with s and with g equal to minus of s g q t f plus fg at a b. This is what we found out. You understood this? I'm sorry for a notational change. Okay, so just to be, if you are getting confused, let me do that. So I'm starting with the partition p, so that for every partition q finer than p, this happens. So fix the partition q, then look at a new partition q1. Okay, now I'm looking at s of q1. Yes, okay, s of q1 with the new, the tags s with the integrator g is nothing other than yes, the Riemann sum for g with respect to the partition q. Q is, remember, q has only x0 to xn, okay, as the tag, as the nodes, and t1 to tn as the tag. So this and fg at b. Is that clear? Right? Therefore, but what we know, s of f q1 s g, because q1 is finer than q and q is finer than p, therefore this minus a is less than epsilon. That shows this fellow is less than epsilon. Minus s g q t f plus f of b minus g of b into g of b minus f of a into g of a. Okay, minus a is less than epsilon. This is for every partition q which is finer than p, and for this any set of tags in q. You understand this? Yeah, right? Therefore, what does it say? So minus integral g df exists, and it must be equal to this fellow. You follow that? Therefore, this must be equal to this. So the theorem is proved. Okay, please pause, review, and proceed. Okay. If there is some sign problem, I'm sure that all of you are good. Okay, you can fix it on your own. Okay, so this is approximate to this integral, therefore this is equal to this. Therefore what does it say? Okay, this says, okay, minus of this must be epsilon close to this, right? That is why I have to take a minus, that is a minus f of b g of b plus f of a g of a. Okay, minus integral a to b g df equal to this. This is what I have proved. You understand this? Therefore you take a minus sign and apply, you get whatever result you wanted. Okay, please go through the proof. This is certainly the final last lecture of the series. Okay, you can see how the proof is very elementary. Okay, and this also teaches one trick. See, most often students, what they do, the textbooks always write the most general case, right, with too much of notation. So you try to understand as it is. With too much of notation, there is a possibility the basic idea may be hidden. You may not be able to appreciate what is the basic idea. You follow that? Yeah. But what I did, I simply I took a simpler case. Instead of x1 to x0 to xn, I to simply take x0, x1, x2, x3. That's it, right? So I tried to see that and try to see. Now you naturally you can see how to do the general case also. Okay, but otherwise what will happen is, if you look at, for example, Apostle, he will give a proof. He will simply write this equal to this equal to this, subtract or add or something, then you will get something. Okay, so people try to either memorize or say that okay, one can check it, so let us accept it. Okay, whereas what you should do is always look for the simpler thing, simplify the notation. Okay, and do it. Okay, but don't make it too simple. Okay, because the intricacies should come out. For example, you could have actually simply taken a, x1 and b as a partition. B, you understood that? Yeah, at the partition q, I could have taken a, x1, b, and then to do that. I just wanted to see it. Okay, so I wanted to put at least 3 subintervals. Okay, a, x1, x2 and b. Okay, so always look at this way. Whenever you look at very general abstract theorem, try to look at some way of simplifying the notation. Look at the simpler case, but don't look at the most simplest case. Okay, it may not give you an idea what is happening, this kind of cancellations, this kind of thing, what is really happening. Okay, if you do this, then you will be convinced. Okay, I hope all of you should be able to write the general proof now. Can you do that? Try. Okay, all the best. Okay, we'll stop.